Greetings, math fans. All right, this is day 7, and today we're going to talk about continuity. And the first part is going to be continuity at a point. So continuity at a point. Okay, continuity as in continuous. Okay, and we got two things to talk about here. First of all, we're talking about interior points. And basically the limit as x approaches c of f of x is equal to f of c. Okay, so this is of course a two-sided limit. And basically what it's saying is the limit from both sides, that has to be obviously equal in order for the two-sided limit to even exist, and that it has to be equal equal to the value at that point also, right? F of c means I'm at that point, so the approaching has to be equal to at the point. All right, so that's important for the interior point. For end points, the left endpoint, okay, the limit as x approaches a from the positive side of f of x has to be equal to f of a. Okay, and for the right endpoint, limit as x approaches a from the negative side of f of x has to be equal to f of a. Okay, so basically they're saying for the left side, or for a left endpoint coming from the right, that limit has to be equal to what it is, the value when you're there. Okay, same thing with the right endpoint. As you're coming from the left-hand side, has to be equal to the value when you're at that point. That's what the f of a is. All right. So let's. I want to start with an example here, and it's all going to be based off of this graph. So I'm going to try and write a little small because I have to make a lot of points here. And here is your graph. Okay, actually I'm going to forward quickly through this. Okay, so here's our graph, and let's take a look at all the different points that we have here. So the first one is going to be x equals -2, which is an endpoint. Okay, and what you're going to tell me, is it continuous there, or is it not continuous, or we call it discontinuous? And at x equals 2, it's continuous. And the reason is because limit as x approaches -2 from the positive side is actually equal to 0, right? And the limit as, or I should say f of -2 is also equal to 0. So that limit as it's approaching it is 0, and also f of 2 is 0. Since these are equal, it's continuous. Okay, the next one I'm going to look at is x equals -1, and this is an interior point. That is discontinuous. Okay, it's discontinuous because the limit as x approaches -1. Okay, and again, it's an interior point, so limit as x approaches -1. Do you guys agree? It's definitely equal to 2. So that's good. It's not doesn't not exist. All right, but f of -1, that's going to be that dot right here. Kind of highlight that. That's going to be this dot right here. That's equal to 1. These are not equal, so that's why this is discontinuous. Okay. Next one is another interior point at x equals 1. And if you look at 1, we have a jump over here, right? It's not the same thing. So again, let's kind of look at what we have. This is going to be discontinuous. I'm just going to write DC just to kind of abbreviate a little bit. And that's, if I look at the limit as x approaches 1 of f of x, does not exist. Okay, because one is -2, the other one is +2, right, for the one-sided limits. So since these are not even equal, this is discontinuous. Okay, and if I even ask you, what is f of 1, you would tell me negative 2. Okay, let's look at x equals 3. It's another interior point. Well, we're right here at x equals 3. Well, it's a very nice point. Okay, that looks continuous to me. If I look at the limit as x approaches 1, the two-side limit is going to be equal of f of x equals negative 2. And what is f of, it's actually x approaches 3. What is f of 3? That's equal to negative 2. So these are equal. Okay, cool. So that's continuous. Couple more. X equals 4. Okay, now again we're talking about endpoint, and you're looking at the limit as x approaches 4, and this is from the positive side, and that limit is right over here. I'm approaching 0, so of f of x, that's equal to 0. And of course, what is f of 4? Well, that's this point up here, right? That's the dot when I'm there. So f of 4 is equal to 2. These are not equal, so this is discontinuous. Okay, and then the last thing I want to talk about is what do I say x equals 5? Well, that's actually, we're going to say that's discontinuous right away because that's not even the domain. Not in the domain. Okay, so it's not in the domain, it's not continuous there. Alright, so that's continuity at a point. Let's talk about continuity as a function. So if I have a continuous function, basically outputs vary continuously with inputs and do not jump from one value to another without taking on values in between. Okay? So basically what I mean by that, it says outputs vary continuous with inputs and do not jump from one value to another without taking values on values in between. So if I use basically a pencil and paper, okay, so I pencil and draw a continuous function basically you never lift the pencil. So if I draw a nice function here like this, okay, that's a continuous function. I never lifted the pencil. As soon as I lift the pencil for any reason, whether it's a hole, an asymptote, piecewise function, whatever, as soon as I lift it, that location is now discontinuous. Okay? And that's what we're going to talk about here now. So let me delete this and continue on here. Okay, here's another graph. I'm just going to talk about a bunch of graphs. And here's a graph. So this is 1, 2, and 3. And there we go. Just a nice little friendly graph. Now what you're going to say is it is discontinuous at x equals 3. And there's different types of discontinuities. This is called a non-removable discontinuity. Okay, non-removable means I can't, it's kind of a simple term, I can't assign a value to plug that hole to make it a continuous function. So can't plug the hole. Okay, I can't plug the hole with one value. You can't just draw a line straight up. Okay, so non-removable means I can't remove it by just assigning one value to that. All right, so we have this. That's a generic name for it, non-removable discontinuity. We also call this And here, another reason too, just to say, is the one-sided limits are not equal. Okay? This is also called a jump discontinuity, because it jumps from one value to another. Okay? All right, let's try another graph here. If I go like this, all right, this is not continuous, or it's discontinuous at x equals 3. This is called a removable discontinuity. Okay, because we can plug the hole. Interesting how we use the word hole. We can plug the hole. All right, so that's exactly what that is at x equals 3. It's a hole there. So it's removable. I can actually assign a function or assign a value to make it a continuous function. But we're going to get to that in a second here. So again, this is a removable discontinuity. The one-sided limits are equal for this one. Okay, that's kind of makes it a one-sided limit, and sometimes you refer to it as a hole discontinuity. Okay, here's a question for you though, and I kind of gave it away already a little bit. What makes a function continuous? What makes a function continuous? Basically, you assign, this is the answer, you assign f of 3 equal, if we make this negative 1 here, we assign f of 3 equal to negative 1. So this could even be like a piecewise function where I give you a function, okay, and it has a hole there, but then I say, oh, gee, and when x equals 3, f of 3 is equal to negative 1. That would actually plug that hole, and that would make the function continuous. All right, so nothing really rocket science. You're just kind of plugging that hole. All right, so let's do a couple more graphs here. Okay, so we got an asymptote there, asymptote there, and then my graph is going to look like this. Okay, and you're going to say it's discontinuous, again at x equals 3, and this is called a, well, first of all, it's non-removable because I can't just plug the hole by assigning a value, so it's non-removable discontinuity. I'll write DC. And we also call this an infinite. This is just another name. Again, the non-removable is more of a generic term. Infinite is the actual type of discontinuity. So it's an infinite discontinuity. Okay, because basically we're talking about an asymptote. All right. Let's do another function here. We're going to do another asymptote here. But this one's going to look like this and this. We can even have an asymptote here if you want. Okay, but what am I interested in? I'm interested in this asymptote here, right? Okay, because it's not continuous there. And of course, this is really the same thing. It's discontinuous at x equals 3, and is a non-removable discontinuity. And of course, this is another infinite discontinuity. Okay, so again, we're talking about the asymptote there. All right, let's take a look at some graphs that were common, some common graphs here. So if I give you y equals the square root of x, and I ask you about its continuity, what would you tell me? Well, this graph, if I would actually graph it, it would look like this. And isn't it continuous? Is it continuous at 0? Well, sure it is. That's an endpoint. And is the limit, as we're approaching it, what is it approaching? It's approaching 0. And what's f of 0? It's 0. So that's good. That endpoint is good. It's discontinuous. So discontinuous, DC, at between negative infinity and 0. Not including 0, right? Including 0 is still continuous. So it's discontinuous at those values. And what is this discontinuity? Of course, that's non-removable. And why? Because it's not in the domain. Okay. What about this one? Y equals the cube root of x. Well, if I sketch that, this one looks like this. Ah, very interesting. This is a continuous function. Okay, so it has no discontinuity. All right, that's pretty reasonable. Let's move on to another one here. Y equals 1 over x. Again, you guys should be good at graphing these now. Especially when you have a rational function, you got to draw some asymptotes. So I know I have a vertical asymptote at x equals 0. And I have a horizontal asymptote because the degree is bigger on the bottom, it's automatically y equals 0. So if I graph this thing, I get, I'll use a red to do my asymptotes here. Asymptote there, and asymptote there. And if you should know how to graph this, but if you're having a little trouble, pick points on either side of the vertical asymptote. So x equals 0, we got to pick -1 and 1. And if I put a -1 in there, of course I get -1. If I put a 1 there, I get a 1. So plotting some of these points, a point here, and I get a point here. But again, you guys really should know that that is my graph. Okay, and now let's talk about discontinuity. It is discontinuous at x equals 0, because really I'm concerned with this guy right here. And it is an infinite discontinuity, and it's also non-removable discontinuity. All right, not bad. Let's look at y equals 1 over x squared. Well, again, if you graph this thing, I know I'm going to have a vertical asymptote at x squared equals 0, so x equals 0, and a horizontal asymptote at y equals 0. So same deal. Let's graph a couple things here, there. And, again, if you're not really sure about it, plot a couple points. We have our 0 and that's our asymptote. We can plot -1, -2, 1 and 2. -1 squared is 1, 1 over 1 is 1, -2 squared is 4, so 1 over 4 is 1/4. And these are the same thing, 1 and 1/4. So what this is looking like is this graph right here. All right. It's of course discontinuous at x equals 0. It's non-removable discontinuity, and it is also an infinite discontinuity. Pretty mellow. All right, let's talk about piecewise functions. If I give you a piecewise function like this, right? Two different functions. Okay, do you guys agree this is discontinuous here? Okay, what type of discontinuity is it? It's a jump discontinuity, and it's non-removable. Okay, because again, you can't just plug the hole. I can't say, oh, I'll plug a hole here because I have a big gap in between here. So you can't just plug it. It's not really just like a hole on a line where you can plug it. So it's definitely non-removable. So do you guys agree that all piecewise functions pretty much are non-removable, there's a discontinuity. Well, it's not really true. Here's an example. Here's a piecewise function, and then there you go. So that's my piecewise function. Okay, so what do you have to do? What have I always told you to do with a piecewise function? You got to check points. Check the points where it changes function. So check the points where the function changes. Okay? And it's kind of like checking your endpoints right there of each of those functions. And sometimes it connects. And if it connects, it's continuous. If it doesn't connect, it is not continuous, and there's a discontinuity at the point. All right? Let's talk about some more functions here, math fans. Y is equal to 2x plus 3 over x minus 1. All right? It is discontinuous. Well, let's kind of look at it. First of all, if I want to graph this thing, it's not a bad idea just to graph it right away. I have my vertical asymptote at x equals 1, right? So the bottom equals 0. Horizontal asymptote, same degree, so it's 2 over 1, so it's y equals 2. And if I graph this, vertical asymptote at 1, horizontal asymptote at y equals 2, and then if I plot a few points, so let's do that, x and y, we're going to do 0 and 2. So if I put a 2 in there, or 0 in there, I get 3 over negative 1, which is negative 3. If I put a 2 in there, I get 4 plus 3 is 7. 7 over 2 minus 1, so 7 over 1 is 7. So 0, negative 3, right here. And 2 comma 7 is somewhere up here. So I know I kind of ran out of room here, but this is what my graph is going to look like. Somewhat like that. Okay, just we're getting a rough sketch. And now you kind of have an idea. I say, well, this thing is discontinuous at x equals 1. And why is it discontinuous? Because it has a non-removable discontinuity, and also we can call it an infinite discontinuity. All right, it's not bad. Remember, at an asymptote, it's not continuous there. Okay, that's important. It's an infinite discontinuity, non-removable. Okay, let's take a look at another function. Y equals x squared plus x minus 2 over x squared plus 5x plus 6. Okay, now I know you guys, if you actually did on your graphing calculator, and let's pull up our graphing calculator for a second. Okay, so let's put this function in. We have y equals, put it in parentheses, x squared plus x minus 2 divided by x squared plus 5x plus 6. And let's do zoom standard. And that's our graph. Okay, so that's very interesting. You know, it's a it almost would look like, if we go back to our original function here, actually here it's on top here, y equals x squared plus x minus 2 over x squared plus 5x plus 6. Doesn't it look like it should have two asymptotes, right? Because we have an x squared on the bottom, and if I set that equal to 0, I'm going to get x plus 2 and x plus 3, so I should have an asymptote at negative 2 and negative 3, but it doesn't show that, does it? It shows I have one at negative 3. That's kind of interesting. Let's actually do a second calculate. Let's put a value in, because what's going on at negative 2? Let's put negative 2 into that. Interesting. Okay, it doesn't give me a value. So what's actually going on at negative 2 if it's not an asymptote? Maybe a hole. That's kind of interesting. All right, well, let's check this out a little closer now. If I factor this, I get y equals x plus 2, x minus 1 over x plus 2, x plus 3. Ah, look at that. That cancels out. Whenever you cancel something out, math fans, you remember that's a whole. So truly what your graphing calculator is doing, it's graphing x minus 1 over x plus 3. Y equals that. All right. So let's actually graph that ourselves. We know we have a vertical asymptote at x equals negative 3, and we have a horizontal asymptote at x squared over x squared, or in this case you can look at x over x, right, at y equals 1. So let's graph that. Y equals 1 is a horizontal asymptote, and x equals negative 3. And then if I want to pick a couple points here, I'm going to pick, again, we're picking around our vertical asymptote, and so negative 3, we're going to pick negative 4 and negative 2. So negative 4 gives me, plugging it into this one, of course, because I simplified it, I get negative 5 over negative 1, which is 5. And if I put a negative 2 in there, I get negative 2 minus 1 is negative 3. Negative 3 over 1 is negative 3. So it's negative 4 comma 5. It's up here. And negative 2, negative 3 is here. So what my graph looks like is this and this. Ooh, missed the hole, or missed this my point that I plotted. All right. But now what I want to do is I need to take into account this guy right here, the hole. Don't you agree there's a hole actually at x equals negative 2? I know I plotted this point here into our function, but that's okay. Now let's look back at it and we'll say, oh, at x equals negative 2 we have a hole. So I'm actually going to erase this little point right here, and I am going to draw a hole at x equals negative 2. Okay, so that's what our graph looks like. Now, let's take a look at continuity. Okay, so I have 2 points, and this is what you got to be careful of, math fans, because on a quiz or test, I'm not going to have 2 blanks for you. I'm not going to give it away and say, oh yeah, I got 2 blanks, and you guys figure out where it's discontinuous. I'm going to have 1 blank, and I'm going to say, you tell me where it's discontinuous, and if you actually do all the work and you don't tell me about the hole, you're going to lose a lot of the credit for it. So what you need to do is you need to look at that asymptote, and you say, oh, so it's discontinuous at x equals negative 3, and of course it's an asymptote, so it's a non-removable, and it's also an infinite discontinuity. Okay? So that's what you're going to put on the answer blank, and then you're going to put on the answer blank, or below that answer blank, it's also discontinuous at x equals negative 2. And the reason is because it's a removable discontinuity, and you can also tell me it's a whole discontinuity. Okay? So, like I said, there's, in this case here, there are two locations where you had discontinuity. One happened to be a whole, and one happened to be an asymptote. All right? So that's it, math fans, for continuous functions for day 7, and have a great day. Adios. Goodbye.